Hi there! Welcome to the emergency review of the Sequences formative assessment. The formative assessment has informed us that we need to review some of our key skills for sequences once again. And that's what this video is all about. So congratulations on being here. This shows your great resilience and growth mindset. You certainly want to learn from your mistakes and make sure you improve at these key skills from sequences. So let's get started. We are going to follow the format of doing a question from the formative assessment and then giving you a chance to try a question kind of like it to see how you do. So here's the first one from the assessment. Let me guide you through it. Take notes on the page you have, and then you will try one just like it in a moment. Okay, so it says we are given this sequence, given by this rule, for n values greater than or equal to 1. That means we can begin with term 1, term 2, and so on, because it tells us n must be 1 and greater. Okay, write the first three terms. Well, we can simply put n value of 1 into here, n value of 2 into here, and see what we get, because this rule creates our sequence. So let's try that. Here's our rule. Here is u sub 1. So I've substituted 1 for n, because n, again, can begin at 1. So I put 1 in here, and there's another n here, so I substituted 1 there. So u1, or u sub 1, is our first term, is found by doing 7 minus 3 times 1 squared. 1 squared is 1, times 3 is 3, so 7 minus 3 is 4. Now, I want you to notice also that the command term here is right. When we see the command term right, it simply means that the answer is so easy to find that you don't even need to show work and you can just write it out. That's kind of what that means. And that's the case here. The expectation is that you can just simply plug in or substitute the values of n right into here, and in your head, calculate the value. So if I do that here, I'm going to put 2 in here next to get u sub 2. 2 goes in here, so 2 squared is 4, times 3 is 12. 7 minus 12 is negative 5. Let's try that for u3. u3 is negative 20, because I put a 3 in here. 3 squared is 9, times 3 is 27, and 7 minus 27 is negative 20. So I'm writing out the first three terms, 4, negative 5, negative 20, and the sequence would continue. We could keep doing that with any n value. Now it says, find the term that has the value negative 761. So this is term 1, and it has a value of 4. This is term 2, and it has a value of negative 5. This is term 3, and it has a value of negative 20. We are looking for the term that has this value. So sometime in the future, if you follow this sequence, it will get to the number negative 761. When we look at our rule, we're not given the n value here. Negative 761 is not the n value. The n value is the term number. We're not looking for term number negative 761. We're looking for the term number when that number occurs. So we're going to put negative 761 here, replacing the un with that. And that's saying sometime in the future it will be that value when. The n value will tell us when. Now solve this backwards. I saw this error very commonly made on people's tests. We have a 7 here. We have to subtract 7 from both sides. And when you subtract 7 from here, you get negative 768 because it becomes a larger negative number, equals this. Next, since this is multiplication here, we're going to divide by negative 3. And when you divide both sides by negative 3, you get 256 equals n squared. Finally, you'll take a square root on both sides to get n equals 16. All right, try the problem like this. Same kind of problem. Let's see how you do. Now let's check our answers. So u1 is negative 1, then negative 13, then negative 33. That's our sequence. Using this rule and simply putting 1 in there, a 2 in there, and a 3 in there. I hope you had some success. Next, what term has this value? So we're going to do the same approach. We say, that's the value we're looking for. We set it equal to our rule, and we see when that happens. Solving it backwards, minus 3 on both sides to get this. Divide by negative 4 next to get this positive value, and take the square root finally to get this. I hope you had success with that problem. Let's keep going. Next one from the assessment looks like this. It says, given the recursive rule, and remember, recursive rule will always look something like this. It will have un plus 1 here, and then a un here. Or sometimes you'll see un here, and then un minus 1 here. The point is, you kind of have un on both sides of the equation instead of just n. Okay, and what that means is you need to know preceding terms to find the next term. So let's see how this works. And also, you need to know some term to begin. Here we're given that u1, the first term, is 17. So write the first 4 terms. Okay, here's the rule we were given. I'm just going to try to put an n value of 1 into that whole rule. Okay, so I'm saying if n equals 1, what happens here? Okay, if n equals 1, if I put a 1 here, I get u sub 2, because 1 plus 1 is 2. And then I can put a 1 in here. So here's what happens when I put n equals 1 in there. Again, this became 2, and this u sub n is now u sub 1, because we put 1 in for n. So this is what we have when we put n equals 1 in there. So what that is telling us, to get the second term, we have to plug in the first term. Okay, then that's how recursive rule works. We need to know the previous term to find the next one. So this makes sense. We need to know u1 to find u2. Well, good news. We know u1. It's right here, 17. So u2 is 2 times, and then 17, I replaced u1 with that, minus 4. 17 minus 4 is 13, times 2 is 26. Now u3 can be found the same way. Now we're going to make n equals to 2. So when n equals 2, our rule becomes this, because when you put a 2 here, you get 2 plus 1, which is 3, so u3. And if you put a 2 here, you get u sub 2. So again, we can clearly see the recursive nature of this, right? To get u3, the next term, we need the previous term. And we just found it right here. So now we're going to put that 26 that we found right here, and we're finding u3. 26 minus 4 is 22, times 2 is 44. All right, and you can continue that process, but I'm going to do it in my head, because again, it says write. The command term write means it should be simple enough for you to just do it in your head. So I'm going to take that 44, I'm going to put it in here. 44 minus 4 is 40, times 2 is 80, and then there is our sequence, 17, 26, 44, 80. I have written the first 4 terms of the sequence, and I've included the one it gave me, which is 17, because that is still one of the first 4 terms. Okay, I hope that process is clear, because you're going to try again right now. So try this problem here. And now let's check our work. So same idea, there's the rule. We're making n equal to 1 first. And when you make n equal to 1, you get u2 here, you get u1 here. We know u1 because we're given it here, right here. So 13 goes in there, and you get u2 is 33. If you continue, u3 should be 93. So check that. If you got it wrong, check that work carefully. And therefore, we have the first, it says first 3 terms. So we have 13, 33, 93. Pause if you need to. We're going to move on. All right. Here's the next one from the assessment. It says, consider the given sequence. And then it says, use the linear approach to create the explicit rule. And then use the arithmetic approach. We've talked about that linear sequences and arithmetic sequences are the same thing. Okay? But we kind of approach them in different ways. And that's what I'm highlighting here. Can you look at it the 2 ways we've seen it? So let's take a look. First of all, the linear approach. Okay, so we have our sequence here. A linear sequence will always have a constant change from term to term. Let's take a look here. To go from negative 18 to negative 14, we're adding 4. To go from negative 14 to negative 10, we're adding 4. And again, adding 4 here. So we do see that constant change term to term. That tells us it's a linear sequence. Now, when we talked about this in the from the linear perspective, that constant change is our slope. So you may remember, basically, a linear equation looks like this. Y equals mx plus b. The m is our slope. So we know that 4 is going to be our slope number. The b is our y-intercept. Now, when we talked about y-intercepts, we said this is term 1. So that's like saying when x equals 1, this is our y value. But when we need a y-intercept, we need x to be 0. So instead of looking at term 1, we're going to go back to term 0. And if we went back in time in this sequence, since we're adding 4 this way, to go back in time, we're subtracting 4. Our term 0 would be negative 22. So now, writing our linear rule, we're going to write it in sequence language. So instead of y, we'll use u sub n equals 4n, because that's our slope figure, the constant change, minus 22, which is the value of our term number 0, which would be like the y-intercept. Okay, that's the linear approach. Now the arithmetic approach. Again, they mean the same thing, they lead to the same thing, but we approach them in different ways. So linear approach, we began with like the ideas of a line, slope and y-intercept. Here, with arithmetic, we begin with the the general rule for any arithmetic sequence, which looks like this. U sub n equals u sub 1 plus n minus 1 times d. Now let's put in the values we know. We know our first term is negative 18, so it goes here. Replaces u sub 1. N minus 1 remains, and our d value is the name for that slope number, that constant change. In this case, it's called the common difference, the difference between terms, and we substitute for d 4. We put parentheses around that to make sure we know this is multiplication. Now that and that do not look the same. So the last part of this question says, simplify this rule to show that it is the same as in part A. We're supposed to show that this and this are actually the same because they don't look quite the same right now. So let's simplify this. Okay, to simplify this, we're going to multiply this 4 through these parentheses. So the 4 will multiply the n and also the negative 1. So we have negative 18 plus 4n minus 4. Now that negative 18 and that negative 4 can combine to become negative 22. Notice now they are the same. So linear approach, arithmetic approach gets you the same place, but you need to be familiar with both to have that big, broad understanding. All right, try the same thing with this question here. Now let's check how you did. So here we have our sequence. I see a constant change of negative 11. It's always going down by negative 11. So linear approach tells me the negative 11 will be our slope. But I also need term 0 for my y-intercept. So this is going down by 11. So I'm going to go up by 11 to get this original term 0 value. So negative 11n plus 34. There's the slope. There's the y-intercept. Let's try that in the arithmetic approach. U1 is 23. The d value is negative 11. Now it's really important you have the parentheses. I saw a lot of work on the assessment or the formative assessment where people did not put these parentheses, and then it just looked like minus something at the end. But you need to put the parentheses to show it's multiplied by that value. Okay, really important. So now simplify this. Okay, negative 11 times n is negative 11n. Negative 11 times negative 1 is positive 11. Combine the 23 and the 11 to get 34, and we notice we have the same rule here. Great job. Hope it went okay. Let's look at the next one. Next one from the assessment looks like this. Now we're talking about a geometric sequence. The last one was arithmetic, now geometric. So let's create an explicit rule for this sequence. Let's first check if it's geometric. Well, when it's geometric, first of all, we are going to use this rule, this general rule. U sub n equals u sub 1 times r to the power n minus 1. R represents what's called the common ratio, or the number we are always multiplying by. Okay, in an arithmetic sequence, we're always adding or subtracting the same number in the sequence. In a geometric sequence, we're always multiplying by the same number. So how do we find that r value? Well, here's how we do it. It's always the same. You can do u2 divided by u1. Or it could be u3 divided by u2 as well. It's basically one term divided by the previous term will tell us what we multiplied by to get there. So in our case, negative 5 divided by negative 2, that gives us 2.5. What that tells us is to get from here to here, we had to multiply by 2.5. And then to get from here to here, also multiply by 2.5. So that is our r value, our common multiplier, our common ratio. So now if I rewrite this rule, I will write it like this. In our sequence, u1, our first term is negative 2. Our common ratio is 2.5, which I just found by doing this, 2.5, and then to the power n minus 1. A common mistake I saw also in the assessment was students were doing like the first difference and then the second difference for geometric sequences. They're doing the little triangles, finding the first difference and so on, and then they're doing a ratio based on that. That's not how we find the ratio. The ratio is found just by what we did here, dividing one term by the previous term gives us our ratio. So here it is. Now that we have this rule, we can find u6. So u sub 6, the sixth term, okay, substitute 6 here and 6 here. So 6 goes here, 6 goes here. That means we have negative 2 times 2.5 to the fifth power when you subtract those. And that on your calculator can be entered as negative 2 times this to that power. Make sure you know how to do that. And we get this value here. So that's our sixth term. All right, hope you feel okay with that. Try the same thing for this one right here. All right. Now that you've tried this one, let's see how you did. So again, you're told it's a geometric sequence. So right away, you know, you're going to use your rule for a geometric sequence, which always looks like this. And we're looking for the R value. What is that thing we're multiplying by every time? How do we find that? Again, we do second term divided by first, or third by second, or so on and so on. In this case, 3.6 divided by -3 tells us we're going to have a negative R value of 1.2. Write the rule now with all the things you need in it. So again, sorry, that means we're multiplying by -1.2, multiplying by negative again. And that makes sense. In our sequence, we began with a negative number, then it's positive, then it's negative. So it means we multiplied by negative to make it positive. And then when we multiplied by negative again, it made it negative again. It's going to alternate, negative to positive. So now our rule must be this. Our term 1 is -3. Our common ratio or multiplier is -1.2. Make sure that is also in parentheses. It's important to have those parentheses because then it means that this exponent is applied to this entire ratio, which is what it should be. If you had no parentheses, that would imply the exponent is on the 1.2 and the negative sign is applied afterwards, but it's not. It's part of this number here. All right, now that we have the rule, we can find u sub 9, the ninth term. So substitute 9 in for n here, and let's solve. Here it's just a matter of punching things correctly in your calculator. So it's really important you got this right. On your calculator, you need to have this negative sign. So you would use the negative button, not the minus sign, but the negative button. And over here, you definitely needed the parentheses on your calculator, or else it would not give you the right answer. So let's see what happens. That should work out to -12.9. How did you do? Okay, next one from the assessment. Same problem, the same sequence we had above there. We have the rule already, which is this, right? We made the rule in the last part. Now it says find the term that has this value. So just like we did before with the arithmetic/linear sequence, we are looking for when does this value occur? And this value is one of the terms in the sequence. So we replace u sub n, which is any future term in the sequence, with that number that we're given. We set it equal to our rule, and now we're going to solve for n, because n will tell us when that occurs, right? When does this term occur in our sequence? N will tell us when. Like, if n is 10, it means it happens at the 10th term, and so on and so on. So let's see. That I can simplify. I have -2 times this ratio here, so I'm going to divide both sides by -2. And when you divide by negative, you can see the negative sign disappeared, and this became half of itself, right? So now we have this. Now, to solve this, to solve any equation where the unknown or the variable is in the exponent, we need logarithms. We haven't quite studied that yet, so don't worry about it. For now, we're just going to use kind of a guess and check technique. So I'm saying here, I have 2.5 to some power has to equal this number. So I'm going to guess some powers, right? I'm going to try, I randomly picked 5. I said 2.5 to the 5th power, and that produced this number. Well, that number is not quite this number, right? So I'm going to need 2.5 to some higher power. So I tried some other things, and eventually I tried 2.5 to the 8th power, and guess what? It gave me that number there exactly. So in that case, I know that this exponent must be 8. Now, that doesn't mean n is 8. That just means this exponent is 8. So it means n minus 1, this whole part must be 8. So n minus 1 must be 8. Therefore, add 1 to both sides, n must be 9. So that means term number 9 is the one that will look like this in this sequence. And if you remember, the sequence is multiplied by 2.5 every time. So if you kept multiplying by 2.5, you would get to this number at the 9th term. Okay, so try this one for your sequence. Try to find this term. Okay, same process. We had our rule already. Remember, these parentheses here were important. We want to figure out when that term in the future is equal to this, and we're going to solve for n. Divide by -3 first, so it's going to turn this positive. And then, again, you can guess and check. So you guess and check some power of -1.2. Again, in parentheses, it's important. So I tried 6, and it produced this small number. Okay, that small number is pretty far off of this one. So I knew that's not going to work out. So I tried a really much bigger number. And eventually, I tried some other numbers. I got to 20. And 20 less power on that gave me the number I need. So again, that means this n minus 1 must be 20. And therefore, n equals 21. Next one, from the assessment, we have 2 quadratic sequences. We have to make a rule. We've practiced this skill a lot. Let's go through the process here without like the tables and all that that we've used as supports for this in the past. Let's begin. So first step is always to find the first difference. 5 to 5, you add 0. 5 to 7, add 2. 7 to 11, add 4. Okay, now the second difference. 0 to 2 is 2. 2 to 4 is 2. So we have a common second difference. Great. We were told this is quadratic, so we needed a constant second difference. That means it's quadratic. Now, the second difference tells us what the coefficient in front of the n squared is going to be. Remember, quadratic always looks like this, a square power. So 2, we have to divide this number by 2 to get our coefficient, so in this case, 1. All right, then I'm going to continue. So here's our sequence from above. Now I'm going to try 1n squared, or just n squared, because we know that's the beginning of our rule. N squared produces 1. When n is 1. When n is 2, n squared is 4. When n is 3, n squared is 9 and 16 and so on. So n squared, term number 1, 2, 3, 4 would look like this. But our sequence is like this. So we need more. 1 is not good enough. We need 5. So we need to add 4 to make it 5. And here we have a 4, but we need a 5. So we need to add 1. Here we have a 9, but it's a 7. So we need to subtract 2. And here's 16, but we need 11, so subtract 5. Now, what you know about quadratic sequences is the last part of it's always going to be a linear rule. So you look at this extra bit we need to complete our sequence, and you say, this is linear. And what's the rule for this? Okay, 4 goes down to 1, so down 3, and then minus 3 again, minus 3 again. So we can see that this is linear. It's going down by 3 every time. So that's our slope, negative 3. And then you think about term 0. If this is term 1, go back to term 0, that would be 7. So our rule is this quadratic part plus this linear part, negative 3n plus 7. Over here, let's try the same thing. First difference, minus 7, minus 13, minus 19, and then minus 6, minus 6. That negative 6 tells us we have a quadratic, and it also tells us our coefficient must be half of that, which is negative 3. So negative 3n squared. Now, what's the linear part? Okay, here's our sequence, as we have above. Now I know it's going to be negative 3n squared to begin our rule, so I do negative 3n squared. And I try term 1. So 1 goes in here, 1 squared times negative 3 is negative 3. Then I put a 2 to get this. 2 squared is 4 times negative 3 is negative 12, and so on. I filled it in. Now, negative 3 needs to be negative 12. We need to subtract 9 for that to work. Here, negative 12 is negative 19. We subtract 7. Here, minus 5. Here, minus 3. So therefore, our linear rule for this is 2n minus 11. Why? Because this is a linear rule now for sure. We can see it goes up to, up to, up to. It's going up by 2 every time. Therefore, our slope is 2. And then if you go back to term 0, it would be negative 11. Therefore, 2n minus 11. Okay, that's a recap of something you've practiced a lot, so try these two. Let's see how it goes. Okay, let's check how it went. This one, first differences, second differences of 2, tells us we have a coefficient of 1 in front of n squared, because we divided 2 by 2. Then you write your sequence, you put your n squared values here, you figure out what you need to make the sequence work, which is 4, negative 2, negative 8, and negative 14. That is a linear sequence now in blue. It's going down 6 every time, so minus 6n. And if you go back to term 0, it's a 10. So there's our rule. Hope that worked out for you. Try this one too. And maybe you have already. Let's check. So first differences. Second differences of 8 tells us our coefficient in front of n squared will be 4. And then you write your sequence. You write what 4n squared would produce when n is 1, when n is 2, when n is 3, when n is 4. And now you see what you need to do to make the 4n squared sequence become the one we need. In this case, minus 12, minus 7, minus 2, and 3. So that linear rule for this is 5n minus 17. Why? The slope here is 5. It goes up by 5 every time. And if you go back to term 0, negative 17. Great job. Let's try some more. From the assessment, all right, these ones get a little trickier. Let's see if we can do this. We need to write an explicit rule for an arithmetic sequence whose third term is negative 1 and whose seventh term is negative 21. Okay, so we imagine a sequence. First term, second term, third term, on and on, seventh term. We are told the third term is negative 1 and the seventh term is negative 21. So we have something like this. It's an arithmetic sequence. Since it's arithmetic, we know as we go from term to term, we're adding or subtracting a certain value, what's called the common difference, or d value. So if we go from here to here, here to here, on and on, we are always adding some d value, adding a d value, adding, okay? So that's how arithmetic sequences work. So now I want you to look at it this way. We're going to write kind of a recursive rule. So here is our recursive rule. To get u7, to get this number, we can begin at u3. You're always working with a 2 you're given. To get to u7, we begin at u3 and we add 4 jumps of the common difference, right? There are 4 jumps. To get from 3 to number 7, there are 4 jumps. And so u3 plus 4 jumps of d will get us to u7. That's what that equation is saying. This is really important to understand why this works, because this will help you solve this kind of problem every time. So now let's put in what we know. We know u7 is negative 21. We know u3 is negative 1. And then we put plus 4d. So again, to get to this number, we begin at this number and do 4 jumps. 4 jumps of d. Okay, solving this, I'm going to add 1 on both sides. That makes that negative 20. And then divide by 4 to figure out that our d value is negative 5. That makes sense. We're going down by 5 every time because it's becoming a bigger negative number here. That's our d value. Now we need our u1 value. Okay, so to get to u1, over here, we begin at u3, and we go back 2 jumps. So instead of doing plus 2d, I put minus 2d, because we're doing 2 negative jumps right backwards, 2 values of d. And u1 then, you begin with u3, which is negative 1, and then minus 2 jumps of d, which we just found to be negative 5. And that tells us u1 must be 9, because negative 1 minus, these two multiply, become positive 10, and we get 9 here. Awesome. So our rule, this is arithmetic. Here's what every arithmetic rule can be written as, right? Our general rule for arithmetic sequences. And u1 is 9. D value is negative 5. There's our rule. You can simplify that by multiplying here and making it look more linear, but there's our rule. Try this one here. Okay, this one, similar thing. We have the 5th term given to us and the 11th term. And I kind of put ... here because I don't want to draw all the gaps, but there's a bunch of jumps here. How many jumps occur from here to here? To get from 5th term to 11th, how many jumps of d are there? Well, to get to u11, we begin at u5 and we add 6. There's 6 jumps of value of d to get to there. So now let's fill in our equation. 18 equals 3 plus 6 jumps of d. Subtract 3 from both sides and divide by 6 to get 2.5 for d. Now get u1 by beginning at u5 and going back in time, right? u5 minus 4 jumps, right? 4 negative jumps of d to get back to here. And then fill in what you know. u5 is 3, and then minus 4 jumps of d. And you get this value here. Because 4 times 2.5 is 10, so we have 3 minus 10 is negative 7. And finally, rewrite it as our arithmetic rule. Looks like this. I hope you had some success with that. Let's try the next one. Now the next one's the same thing, but now it's a geometric sequence. So we're going to try the same process, but in geometric, we're not adding and subtracting numbers. We're multiplying by common value, right? So let's see how it works here. So here's our sequence, and we are told we have the 4th term and the 7th term. So here's term 4, negative 192. Here's the 7th term, negative 12,288. Okay, and again, you're thinking, again, it's geometric, so this time, how many jumps, but the jumps are not d. In geometric, we call them the r value, and we're always multiplying by the r value, right? We're not adding r, we're multiplying by r, multiplying to get from number to number. So multiply by r once, multiply by r again, multiply by r a 3rd time. And how that works then is this. To get to u7, we begin at u4, and we multiply by r 3 times, right? An exponent means how many times we're multiplying by something, right? R cubed means r times r times r, right? Which is what we have here. So that's our little rule for setting up the connection between these two terms. Make sure again to pause and understand that. So we know the 7th term is this. We know the 4th term is this. And now we're going to solve this. This is going to take a little more thinking here. How do we solve this? Okay, let's see how this goes. So I have this equation. I want to solve it. I see negative 192 times r cubed. There's multiplying here. So to get rid of this number here, I'm going to divide. I'm going to divide both sides by negative 192. That means this number will turn positive. And when you divide it by 192, you get 64. So 64 equals r cubed. Now you can punch down your calculator. There's a way to do cube roots. Pressing the math button, you'll see your ability to do different kind of roots there. A cube root of 64 is 4. What that means is 4 times 4 times 4 is 64. So now our r value is 4. So if you went from here to here, maybe that makes sense. 4 times that will give you some value, times 4 again, times 4 again. It grows very quickly to this number, right? Okay, now we need u1. So to go, I'm going to do the same approach we did before, right? To get to u1, I begin with the one I know. You begin at u4 and you take 1, 2, sorry, I don't see u3 here. It would actually be 1, 2, 3 jumps back. From u4 to u1 is 3 jumps back. And we're not going forward, which would be multiplying. We're going back, so we're actually dividing by r, dividing by r, dividing by r again. So I'm dividing by r 3 times because I'm going backwards. Okay, so u1 equals u4 divided by r cubed. It's coincidental that this is r cubed and r cubed, okay? Don't make some kind of weird connection in your brain that those have to be the same. They're not. It just happens to be that it's the same number of jumps forward here as it is back here. Okay, so u4 is negative 192 divided by r, which we just found to be 4 cubed. If you do that on your calculator, you will receive a value of negative 3. So that tells us we can now write our geometric rule, which looks like this. Our first term is negative 3. We just found it here. Our r value, the common multiplier, is 4. So I write it here. And there's our rule for this geometric sequence. Try this one in the same way. Let's check our work. In this one, we are given term 3 and term 6. There they are. Let's try the same approach. Okay, so you're thinking to get from u3 to u6, how many times are we multiplying by the common ratio? Well, that's 1, 2, 3 jumps. Between 3 and 6, 3 jumps. So our equation is to get to u6, we begin at u3 and we multiply by r 3 times, r cubed. Again, coincidental that that's the same as the last problem. It just happens to be that there's 3 jumps between here and here. Okay, so there's that. Our u6 value is given to us, our u3 value we know like that. Do this. Now you can divide by 147 on both sides to get 343. And then take the cube root of 343. So in your mind, you're thinking, what times itself 3 times is 343? That number is 7. Now let's find u1. To get to u1, we can begin with the one we know, u3 divided by r squared, right? Because to go backwards here, you're going to divide by r once and divide by r another time. Again, forward is multiplying, backward you're dividing. So u3 divided by r squared. 147 divided by 7 squared, because that's our r value, and you get 3. That tells us our geometric rule, which always looks like this, will be 3 times 7 to this power. u1 value, the starting value, and then our common ratio of 7 here. Great job. Let's try the last one. So from the assessment, we had this problem. We are told it is an arithmetic sequence. Okay, this is key because otherwise we wouldn't know what to do with this. But we now know it's arithmetic. In arithmetic sequences, for example, one like this. This is arithmetic. Check it out. How much does it go up each time? Arithmetic means we're always adding or subtracting the same number, right? Here we're adding 6, adding 6. Okay, so the d value is 6. Right? That's our d value. That's called the common difference. Or the slope when we think about it like a linear sequence. Okay, so that's the common difference. But how do we find that? Of course, our brain tells us 6 pretty quickly, but in terms of calculating, how do we find it? Well, to find the d value, we can always do one term minus the previous. 8 minus 2 gives us that d value. Or 14 minus 8 gives us that. So you can do u2 minus u1, or you could have done u3 minus u2, or you could have done u4 minus u3. So let's do that here, right? If this is arithmetic, we should be able to find the d value by subtracting terms also, right? So I'm going to write that equation. The d value equals u2 minus u1. Because again, the second term minus the first will give us the d value. And we can write that here. We can also say the d value is u3 minus u2. Because again, we could have done third term minus second to get the d value. So in this case, that minus that. So let's replace that. From our sequence, u2 is 3k plus 4. u1 is 4k minus 2. So I'm doing second term minus first term. And notice I put the parentheses. Very important we have those. Now this negative will apply to both of these parts in the parentheses. So we have 3k plus 4 minus 4k, and then a negative times a negative here makes a positive 2. Now combine like terms, 3k minus 4k is negative k, and 4 plus 2 is 6. So D equals this. That still doesn't tell us what k is. Okay, so let's try it here. Now we're going to use U3 and U2. U3 is 6k minus U2 in parentheses. Now apply the negative to both parts. So 6k minus 3k minus 4. And 6k minus 3k is 3k minus 4. Now, the next important step is here. Well, this represents the D value, and this represents the D value. We know that the D value must always be the same. It's constant, right? That's constant difference. That's why it's called D value, the common difference. So that must be equal to that. So that's what I do next. I set the two things I found for D, the two expressions, equal to each other. And now I have this equation. I'm going to solve that. So what I did is added k on both sides to get 4k, and then I added 4 over here to get 10. Now divide by 4, k equals 2.5. Now that I know k, I can finish up the problem, which is find U15. The k, okay, so I'm going to put 2.5 back in here to figure out what these terms are. Okay, so when you put 2.5 in here, 4 times 2.5 is 10, minus 2 is 8. And here, if you put 2.5 in here, 3 times 2.5 is 7.5, plus 4 is 11.5, and so on. So now we have our sequence, and we can find the common difference. The common difference is that it goes up by 3.5, up by 3.5 again. So we can write our arithmetic rule using our general rule formula, right? So U1 is 8, we can see it here. Our common difference is 3.5, and we've written our rule. Now that we have the rule, we can find any term we want. In this case, U15. So 15th term will be found like this. I put the 15 in here. 15 minus 1 is 14. 14 times 3.5 plus 8 gives me this value right here. How about you try this one, the very last one? Let's see you do it. Okay, same approach. D value can be found by subtracting U2 minus U1 or U3 minus U2. Great. So this minus that simplifies to negative 2k minus 2, and that negative is applied in both parts. Combine like terms, 4k minus 10. Over here, we have third term, 8k minus 2, minus second term. Parentheses are important. Minus sign applied to this and this becomes negative 6x plus 8. Combine like terms, 8k minus 6k is 2k, minus 2, and 8 is 6. Set those two equal to each other because the D value must be the same, however we find it. Solve this equation. 2k equals 16 by subtracting 2k and adding 10. Divide by 2, 8. K is 8. Put it in here to create your sequence. 2 times 8 is 16 plus 2 is 18. 6 times 8 is 48 minus 8, 40. 8 times 8, 64 minus 2, 62. There's our sequence. We can see U1 is 18. We can see it is going up by 22 every time, so our D value is 22. So our arithmetic rule will look like this, and we're looking for the 13th term now, so using our rule, put 13 in there, and our 13th term is 282. Great job, you have done it. I hope that every single question where it said try one, you were able to do it correctly, because that's the goal here. We looked at the entire formative assessment. We retaught all the questions, making sure you became a master of these processes, and then testing yourself. And I hope when it came time to try one, you really tried it and you're able to do it and you feel much more confident now. Great job. Let's see you next time.